page. We are in module 2, but in layman practical approach, you can see various example of estimation. So just we are going to start. It is lecture number 11, and here we will talk about estimation. So are you able to see the slide? Anyone respond? Okay, fine. So I am saying that estimation is very much common in our practical life. So one simple example, everyone might be aware of our judiciary system. There, people are saying that one lawyer or judge come with some kind of judgment regarding any of the issue. Okay, and judgment, or simply you can say that inference. So if you talk about here, I am talking about in local sense, and it might be a just look my observation. So if you try to see here my observation, it says that in Indian judiciary system, every judgment, either it is just a fluke or simply what we call it bias estimation. There is a bias estimated judgment, because here in our judiciary system, mostly lawyer and judge, they never study computational mathematics. So if someone is just trying to give a judgment just based on observation, then simply you can say that judgment would be biased, or simply it would be a fluke. If it is very much true, then it might be a fluke. It is not very much accurate computed. Okay, so if you want to come someone with very good judgment, then definitely computational mathematics is needed there. If that person know computational mathematics, then definitely judgment would be computationally very good. I'm not saying that very accurate computationally, that judgment would be very good. So anyone can say that do you see any such kind of person who can have very good mathematical knowledge? That means that person is not having very good idea of estimation process and coming with judgment. Anyone know such kind of person? Anyone? No answer. Just through various YouTube and other resources, I came to know that one person is there. Everyone might be aware of that. Subramanian Swami. He is very good in mathematics. But if you try to see him, he is giving very good judgment about many of the cases. But he is not a lawyer. He is not having any degree in law. He is not a lawyer. But he is giving judgment based on his mathematical aptitude and computational, that he is very good in computational mathematics. And if you try to check it out, his degree in mathematics is really very good. One of the, you can say that a very renowned person in the computational mathematics, you can say that. So those things I will talk in detail here. So coming to outline of my lecture, and first I would like to talk about again that recap of sample and sample statistics. So if you are having a sample, then in that sample definitely we will fix a size, and if there is a sample of size n, then we will have n observation. Those n observation are forming a sample. Okay, so now those n observation are what? Those are n copies of the same distribution, same random variable whose distribution we don't know. So these are the n observation. So what is sample statistic? It is talking about any function of these n observation. So if you take any function of if you take a single function of this one function of t is a function of x1 x2 up to xn, then definitely it is a function of random variable. So simply you can say that this distribution, this one will have a derived distribution. And why? Because it is a function of functions. So definitely function of function again happens to be a random variable. So sample statistics here, it is a random variable, but it is a very specific kind of random variable. Here how? Because we are defining sample statistics based on some sample of particular size. So that's why we are giving a name sample statistics. Okay, now I will talk about later what are the estimators. So if sample statistics is directed towards some kind of parameter, that means it is having a job to estimate some kind of parameter, then in that case that sample statistics, it will have a name. That name we are calling it estimator. It will do estimation. Okay, so that's why estimator name is coming. Now if you observe one particular value of that sample, okay, one particular value of that sample, then what will happen, based on that, the big corresponding value of estimator, uh, estimator is a random variable. So with respect to one observed sample, the corresponding value of the estimator, we will call it estimate. So estimate, and so that's where there is a very close relation between estimator and estimate. Estimate is just one, like one value, one observed value of the estimator, because estimator is here a random variable, it is a random variable. Okay, and one more thing you can say that, uh, for a parameter we can have various estimator. Why? Because estimator is always, it is a function of this n, sample size. So if you change sample size, you will have different estimator. So you keep on varying estimator, various, so you will have a collection of estimator, various estimator you will have. But if you try to estimate, then you have to fix sample size. That means you are fixing the estimator, and from there you try to estimate something of your interest. So that is the story. Okay, so and after that, if you are having estimator, then we will talk about various things, because here we are not looking into completely within the population, complete population. That means everything we are not looking, because we are not having all the power. So that's why we are not looking to complete population. What is happening, just we are looking to, based on our computational feasibility, just we are looking to sample only. So that's why from the sample we try to come up with some kind of estimator. Now once we are having estimator, then we will talk about efficiency of that estimator, then we will talk about sufficiency of that estimator. All these are what, these are criterion to validate whether our estimator is the best one or worst one or right one or wrong one. So that thing, so those things are actually established by further, what we call it, all these are very much a criterion kind of thing, or measure kind of thing, that measure whether your estimator is a good or bad. So that is the thing. Okay, so coming to recap of that sample and sample estimate, here I will talk about that once we are having a sample of size n, then due to n number of observation, then we can define statistics, from that statistics we have to lead toward estimator. So something would be in our mind what we want to estimate. Okay, that's why we are just giving, just estimator is another name of one particular name of statistics. So simply we can say that. So we had already discussed that statistics, it is a function of observable random variables which does not contain any unknown parameter. There is no, okay, which does not contain any unknown parameter. There is no any unknown parameter, such as what we can say that, for example, sample mean or sample variance or minimum or many various kind of things we can define. So all these are statistics. Okay, so like I will define it later. So we can say that a statistic can be used to estimate a population parameter. Like if you are having a population of world, and you want to, your parameter is what is the mean height. So mean height is the parameter, and that you can't calculate directly, because in order to calculate mean height, you have to calculate the height of each and every one, and that one is a very tedious job. So what you will do, you will take a sample, and from that sample you will define sample mean. You will define a sample mean that will give an estimate of that, that's population height of the people, okay, in this world. So that would be, so that's way, so that sample mean happens to be one statistics, and that is giving an estimate of one estimate of the population parameter. Okay, in this case the statistics is called an estimator of the parameter. So that's where here this estimate is doing a one estimation of a particular parameter. So that's where we will call this statistics a, an estimator. So that's why I told that just you among the statistics you try to particularize it. So that's why it becomes an estimator of the parameter of interest. Whatever parameter you want to introduce, it will be based on that. Okay, now sample statistics are used to estimate population parameters, such as, one example you can say that this we are defining sample mean. So the definition of sample mean, you might have already seen that how we are defining. So we had a sample size of n. So that means we observe n copies of the uh, suppose height, n copies of the height, that means sample size we are taking n. This is saying that we are doing a random sample, we are taking a random sample of size n, so that means we are observing these n number of copies of that. So how we define n number of observations? Some all these each one having would be what? It would be a random variable. So just sum it up and plus up to xn and divide by n. So you are trying to deduce this from the sample itself. You are not looking into the population, so you deduce this one from the sample. So that's where this name of this one, this x bar, we are calling it, it is again it is a random variable here, because it is sum of random variable, and we divide not to, it would be n. We are taking n number, sample size is n, so it would be n. Okay, so this is the sample mean. So simply we can say that sample mean, it will give one estimate of the population mean. Whatever population mean it would be, so the sample mean will give one estimate of that. So one value of the sample mean, x bar is actually an estimator. It is an estimator, and one value of that estimator will give one estimate of this population parameter. That one is mean. So every statistics is having a distribution, and we call it sampling distribution. So if I'm asking what is the sample distribution of sample mean, then that means distribution of sample mean, it would be what? It would be sampling distribution, and it would have nature similar to approximate normal distribution. So normal distribution is very important to understand all these. So sampling distribution happens to be an approximated Gaussian or approximated normal distribution with corresponding parameter as the mean. So you can say that it is another way of representation of central limit theorem. You can say that. So coming to estimator, and how do this estimator perform estimation, that thing I will discuss in detail. Till now, am I audible? Okay, fine. So we will go further. So in between, if anyone is having any question, you can ask. Otherwise, I will keep on forwarding. So we are calling it. I will first discuss about estimator, and how we do perform estimate by using one estimator. Okay. I will take example as well. So we can say that an estimator is a function that maps a random sample to the parameter estimate theta cap. This one is capital theta cap. So I had told that if you are willing to represent a random variable, always we denote it by capital letter, and the one observed value of that value random variable we denote it by small letter. These are the notational convention, and we have to stick with that. Okay, so here we are calling theta cap, theta hat is actually one estimator. It is a function of that random sample of size n. That means it is a function of n number of observation x1 x2 up to xn, and hence we can say that as this estimator, it is a function of this uh, n number of observation. So we can simply say that an estimator is a random variable. Function of a random variable is always a random variable. So that implication, you can see it like this way, because we say that random variable is, it is a map from sample space to R. Now afterward, what we do, we define a function. uh, we are taking function of this random variable itself. So through composition mapping principle, you might be aware of that. If I'm asking what is the domain of G, domain of G of X, it would be also sigma X. You can sigma, simply sigma. It will go from sigma X to R. From the composition principle, you can apply it here, because it is G of X. You can say that G of X like that way. That composition, so through composition mapping, you can say that the function of a random variable is again a random variable. So that's why estimator is again a random variable. Now, for example, we can consider n number of observation for a sample size of a random sample of size n. then an estimator is the sample mean as follow. We can see that. So if you are having a random sample of size n, a sample of size n simply with n number of observation, then we can define a sample mean how by summing the all the observation and dividing by n, then we are having a sample mean. This is a sample mean, and easily you can say that this sample mean is an estimator. Why? Because it is a random variable, so it is taking various value, various this sample mean, because x1 will take various value. In last example I had already given, I had taken a population as 1 2 3, and for this population we did sampling of we took sample of size 2, and that means order pair 2, and we got various order pair. That very exactly we can say that we got how many order pair? 8 order pair we got, and not 8, 9 order pair we got, because we made a sample of size 2 with these three number. So how many possibilities are there, how many samples are there, so or how many outcomes were there? It was 9. So 9, we got 9 sample of size 2. So whatever the first coordinate, we call it x1, first observation, and second coordinate is in this sampling process we call it x2, that second observation. So that is the same process. If you are going, if you are increasing size up to n, then what will happen? X, so you will get nth observation, starting from first to nth observation. So that scenario is coming. So that's in that process we are defining sample mean. And you had already seen that there was also distribution of sample mean. So if you sum it up, keep on summing, then you had already distribution of sample mean. So x bar was also a random variable. So as an estimate, what is an estimate? Again, this theta is what lower form of this cap. This one is the capital theta. This one is the lower theta. Lower Greek word. This letter. This one is lower Greek letter. So an estimate theta cap is the result of applying the estimator function to an observed value. That means in the estimator function we are how we do. So here in this estimation process we take one observed value of this n observation, one observed value for the sample, one observed value for the sample means one observation of this first observation, one observed value of the second observation, and one observed value of the another observation. That those are x1, x2, x3. That means it is making one observation of the sample of size 2, and in that process if you apply the function, then you are getting a small theta cap, or a small theta hat. So this is what it is, an estimate of theta. It is, we call it estimate. It is an estimate, it is not estimator. So this theta hat, it is a particular value or observed value of capital theta cap, capital theta cap. So that's why we call it estimate is what it is, one observed value of the estimator, simply we can say. So for example, further consider x1, x2 up to xn. It is an observed value of a sample of size n. Then an estimate is the sample mean as follows. So we can define that x bar, a small letter I am taking, a small, it is talking about one particular value, observed value. So one observed value or estimate, you can define for sample mean, you can define like this way. So cap I am using. So going further, I will talk about criteria for validating right choice of estimator. So how we can say that once we come up with some kind of estimator, how we can claim that that estimator would be right choice of estimator, or good or best or worst, what do you want to say? So you need to introduce some kind of criterion approach. So one criterion approach I will go through like this way. So there are many estimators. If you are taking, suppose you want to estimate mean height, mean weight of a person, mean weight of person in this population, in the mean in this population, population of human being, you try to calculate mean weight or try to compute mean weight. So what you do, so you various people are trying to estimate compute mean weight. So definitely it is a very difficult job. So what several people will attempt to do that, definitely people are doing that, such kind of thing they are doing. So they do generally do through sampling approach. So each one will have some so various person are trying, each one will have different size of sample. So that's why if you're taking a sample of size different, then you will get different estimator. If you, another way is taking applying the process of sampling sample of size different, then that would have different estimator. So various estimator you will get. So that's where there are many estimator of the same parameter. If you are trying to estimate same parameter, mean height or mean weight or mean uh, IQ level or whatever you can say that. So various estimator you will see that. So natural question will come, which estimator is the better one? Natural question will come generally. Then a comparative sense, which one is better, with which estimator we have to proceed, that means what is the best sample size. So simply that means what is the tight bound of the sample size. So later we will come to know, so what is the tight bound of sample size. That one is one question. It will be resolved in module 4. So what would be tight bound of the sample sampling, that sampling size, that also you need to know to get very good estimator. So to infer this question, we need to apply various criterion for the estimator. What are those criterion? First criterion is unbiasedness. So that means whatever estimator we are defining or we are going with, then that estimator must be unbiased. So there is a definition of unbiased, don't worry, there is a definition. So all these are measure, all these are criterion. So means that these are having well defined condition approach, well defined, these are all well defined concept. So these are first criterion, unbiasedness. So we have to look whether that estimator for particular parameter is unbiased or not. Second one is talking about efficiency, whether that parameter is having very good efficiency. So unbiasedness, simply you measure it, how you measure it. So simply we come to know that here estimator is a random variable. So if it is a random variable, then we can talk about mean of the, or mean or expectation, both are same. So if you will talk about expectation of that estimator, and if you are trying to find that mean or expectation of that estimator, and it happens to be equal to the true value of the uh, parameter, then we can say that our estimator is unbiased estimator. So this is that means if you this estimator you are taking for mean height, you are trying to compute mean height, and mean this theta is the mean height talking about. And if you find the expectation of this estimator of height, mean height, then our sample height, sample mean height, and if you are finding the expectation of that happens to equal to that population mean height, then simply we can say that this estimator is an what, unbiased estimator. Now next we will talk about efficiency. It is very much explained by variance of the estimator, because estimator is a random variable. So again we can talk about variance of that estimator. So all these are what, well known quantity, well known measure. So all these are measure. So if simply you know that mean is what, it is representative or central element of the data. So if you are having a data, so what you do, you always try to represent that data by some kind of central quantity. So one of that quantity is mean or expectation. That's where you know that it is a very very nice kind of thing to represent a data. Okay, like efficiency we can explain by using variance of the corresponding estimator. Okay, then sufficiency will come, then consistency will come. So all these are having a very particular major definition. So we will discuss in detail. So unbiasedness, first I will talk about unbiasedness. So what is meaning of unbiasedness? A unbiased estimator say capital theta cap has an expected value that is equal to the true value of the parameter that would be estimated. Okay, so that suppose our true value of the parameter is theta, and we are just come up with one estimator, the capital theta cap, and if you are finding the expectation of that, and that happens to be equal to the theta, and that parameter theta, then we can claim that this theta cap, it is a unbiased estimator of the parameter theta. So this is the definition of unbiasedness. This is the definition of unbiasedness. So here example I would like to take. So if you are taking a sample of size n, that means we are having n number of observation, and we define the following estimators. So first we are defining sample mean, So this is the definition of sample mean. How we define? We sum the observations and are divided by n. So in that process, we are getting sample mean. This is the sample mean. And likewise, we do define sample variance. How? We are not dividing sample variance here. In order to define sample one, we are not dividing by n minus n. We are dividing n minus 1. So this is one kind of Bessel correction approach it is coming. Why? Because if you define sample variance by 1 by n with 1 by n division, then what will happen if you try to find the uh, expectation of this sample variance through that definition, then that would be not equal to the population variance. Generally, popular, what is the notation of population variance? We denote it by sigma square. So if you are defining in that way, then it would be, if you use n, then definitely this would be not equal to this. But if you are defining a sample variance by this definition, that means you are taking a square deviation, sum of a square deviation, and you are dividing by 1 by n minus 1, then what is happening? You are multiplying with 1 by n minus 1, or that means you are dividing with n minus 1, then you will see that the expectation of s, that is sample variance, s square is a sample variance, a capital letter I have taken. Why? Because it is an estimator, it is a random variable. So that's why if you're trying to find a expectation of this one, this would be equal to true variance. In that case, for this kind of sample variance, the expectation of sample variance would be equal to true variance, and hence we can say that here x bar and s square both are unbiased estimator. So that is the concept. So next we will talk about efficiency, and here again I will take several examples, because without example, any concept, to understand any concept, example is very much necessary. So efficiency, how we can define? So we can say that we can define generally efficiency by least or mean square error, and there are various other criterion functions. Simply loss function, you can say that it is just concept. Efficiency we generally measure it through loss function. So till now, am I audible or not? Because I'm not getting any question from your side, neither. Am I audible? Okay. Anywhere, if you face any problem, let me know. Definitely I would like to answer, because I'm already recording all these, so you can get a recorded version anytime. If you want to have a live interaction, so during the classes also, only you can get live interaction. So that's why keep on asking question if you are having any problem. Okay, so we will define here efficiency. So efficiency, what, how we define? So an estimator is efficient if it estimates the parameter of interest in some best way, in some best way. And the notion of best way, it relies upon some choice of a loss function. So very simple kind of loss function is quadratic loss function. So various loss function, you might have already seen that generally loss function is induced by norm. So L2 loss function, that means you are because norm, what is talking about, how we can compare two point in Euclidean space, in higher dimensional space. Okay, we can compare by defining some kind of length, generalized length, simply because these are the vector. So the order property is missing there. We can't say that x is greater than y. There is no such kind of concept. So to measure things, we need to introduce a generalized distance that we are calling it norm. So in order to measure the comparison between x and y, so or so we introduce here the notion of distance. So this distance, notion of distance, is coming with respect to norm, and there are various norm 1, norm 2, norm 3, norm 4, norm 5, norm p, norm 0. So various norms are there. So simply norm concept, it might be clear to everyone. So this one is the norm 1. So this one is the norm 1. So this norm 1, you can say that you just walk along coordinate axis, and you are while walking along coordinate axis, then you are measuring the total walk along each coordinate axis. That would be your norm 1. So graphically, if you suppose you are in 2D, and in 2D take one point, like one point, it is here. That criterion function must be clear. That's why I'm again defining explaining norm. So suppose you are here this point, at this point I'm asking what is the length of this point. Definitely this will be a vector. So what would be length of this one? Anyone can comment over this? What would be length of this one? Anyone? Okay, I'm giving name of this point. This point is 1 1. First coordinate is 1, second coordinate is also 1. So what is the length of this one, or norm of this one? I'm giving name to this point A. So what is the norm of A? Anyone? Square root 2. So you know that from, yeah, definitely the square root 2, it is a one norm. And but apart from that, can you define another norm? It is the shortest distance. What you say that and in Hindi there is a muhavra that you walk along the nose, नाक के सीधे चलना. So that distance you talk about. So it is actually Euclidean distance or norm 2. It is norm 2. Apart from that, how you can measure distance? Any other distance? There is one more distance. This axis is x1 axis. This axis is x2 axis. You can call this norm as a taxi cab norm. How we define? So first you walk along a horizontal axis up to how much? One unit, and then you walk along vertical axis in order to reach this point 1 1. Okay, so how much walk you do along vertical axis? 1. So total, what is the total walk? Total walk is 2. 1 plus 1 is 2. That means that distance we are calling it norm distance. So we are just measuring absolute walk along corresponding axes. So this one is also one distance. And later you will see that in high dimensional, all these in any Euclidean space, all these what distances or norms are equivalent to each other. They are having equivalent topology. So it is immaterial with which distance you proceed. So it would be immaterial. You can, any other distance, anyone can say that? Apart from that, have you seen any other distance? So I had already discussed here two distance. First distance is Euclidean, that you know from your high school. Second distance, that taxi cab distance or Manhattan distance, or simply you can say that absolute walk along the corresponding axes. And third distance is what it is talking about relative distance. That means just try to walk along coordinates axis and see which one is the maximum. That would be the distance of that point. So that distance we generally denote it soup distance, or we can say that relative. You can say that, or you can denote it by uh, infinity, this norm with suffix infinity. There is a meaning of that why infinity is coming. And what would be that? Relative distance. If you walk along x1 axis, relative absolute distance walk is 1. And if you walk along x2 axis in order to reach here, absolute walk distance is 1. And hence we can say that relative distance or soup distance, that maximum walk along any one axis, we will take maximum walk along any one axis, which so anyone, so if you take 1 2 point, then 2, that one is talking about walk along the x2 axis. So that 2 would be the norm of that. So that soup norm. So this is the soup norm. Generally we see that. So in general, you try to see the definition of norm. It is coming like this way. If you're taking any vector x, I'm taking any vector x, so p norm, we define it like this way. If you calculate, so what you do, p definitely uh, it will here how it is coming. So x is any n dimensional vector, so x will have n number of coordinate, uh, or x is n tuple. So we take raise the power of xk, each coordinate of the tuple, to p, and we variate varying k from 1 to n, because here x is n tuple, and we take power 1 by p, radical power. This is the radical power. 1 by p. So same thing, how you define it? You define it, it is having two coordinate. So what we do, we are taking a square of one, a square of first coordinate, then a square of second coordinate, and after that we took a square root. So it is the same case that here p you have taken equal to 2, p is here 2, and n is also 2, because this point is two dimensional 2. So that's where you are getting a square root. And if you take p equal to 1, then you will get this one is talking about p equal to 1, then modulus of 1 is 1 plus modulus of 1 is 1. And if you sum it up, how you are getting, 2. So here p is equal to 1 and n is equal to 2. So this one is one norm. That's why norm, name of norm, it is coming with respect to p. So one norm. And if you take supremum or limit supremum, limit p tends to infinity. If you take p tends to infinity, then it becomes what? There is a concept from math 1, you can see that it will becomes max of xk. Which one would be max of xk, where k varies from 1 to n, that dimension of the point, 1 to n max. Which one is maximum? So if you take limit with respect to p, and p tends to infinity, and it will give your this third norm, soup norm. Also name is coming soup norm. Max or soup both are same thing, so you can call it, it is a soup norm. So what is the maximum work among the all the coordinate work? So that would be your soup norm, value of soup norm. So the various norm among these so between, if you take, so here free to take value of p between 1 to infinity, 1 up to infinity. Again there is a abuse of notation, infinity means very big. So you can take here, let me, it is coming like k, not k. So here p may take value between 1 to infinity. Even you can go up to 0 as well, there is no issue. But if you take a norm between 1 to infinity, there is a meaning that this norm is actually convex in nature, very nice structure, that easily you can do optimization with respect to this kind of norm. Optimization is easy. And if you take norm between 0 to 1, then optimization norm would be non-convex, and optimization would be very difficult. So that way people are generally not taking norm between 0 and 1. Okay, so that is the concept of norm, or that is the concept of defining that loss function. So loss function you can define with respect to various norm, whatever norm you want to proceed with. So norm 2 is generally a square law, a square distance. You can say that it is coming with respect to a squaring, p equal to 2. So that's a square. So here simplest to that norm we will take a square. So usual choice of a loss function is quadratic or a square, simply quadratic loss or a square loss, you can say that. So resulting in the mean uh, mean squared error. So what would be that efficiency criteria, that loss uh, criterion, loss measuring criterion? We will have a specific name. That name we are calling it mean squared error criterion, or in short we can say that MSE. And what is the optimality? So optimality we define like this way, we can see it here. So how we define? So we are defining here a loss function by a square or quadratic loss, and that means this is the estimator. This is the true parameter. We try to try to take residual. So you can say that it is the difference, that, or simply estimation error. You can better call it this is the estimation error, and we are taking defining loss function in such a way quadratic, and we try to find a mean or expectation. Expectation and mean both are same. So if you try to find it out, just simplify it. That means add expectation of that estimator, and also subtract. Just you what you do, you are just doing this just for computational what computational point of view. That means you want to give the this mean square error a suitable form. So if you put all this, then if you simplify, then it can be bifurcated into two parts. First part is what? This one, expectation of this deviation, mean deviation of estimator, and plus a square of difference between mean of estimator and true value. So that means it is hazy little bit. So you can say that it is like this way. It is talking a square of difference between capital mean of estimator minus theta. Okay, so this quantity is this. Okay, so in this linear model, it is having an in this estimation process, actually it is having a name. This term we are calling it what? What is this? Anyone can comment over this? Do you know what is the name of this? Anyone? Just see, I told that here is estimator is a random variable, and that hint is enough to explain that what would be name of this. Anyone can say that what is name of this first one? Anyone? Just see it and uh, come to that point, that what is the definition of this. Anyone can say that? No clue. Are you getting meaning of this or not? Okay, come to define variance. So take a random variable, and how we define variance? How we define variance of a random variable? Suppose x is a random variable, and how we define variance? We define variance as a expectation of a square mean deviation. A square of mean deviation as expectation of a square of mean deviation. That means we deviate each value of random variable by corresponding mean of the random variable. We deviate the random variable by corresponding mean, and after that we do a squaring, and after that what we do, we find expectation. We are finding expectation. So this is the definition of variance. Did you get or not? This is the definition of variance. Okay, fine. Same here, I told that estimator is what? It is a random variable, and this term is what? Mean of the that estimator. So simply, what does it will talk about? It will talk about variance of the corresponding estimator. So you can say that it is what? Variance of the estimator capital theta cap. It is variance. I told that estimator happens to be a random variable. So simply this term is talking about variance. So mean square error has been divided into two parts. One part we are calling it variance of the estimator, and second part it is talking about this term is what? It measure, we are saying that it is bias. It is bias. I told that when system is unbiased, when if you are finding mean of that estimator and that one is equal to true parameter, then we say that unbiased. If it is not equal, then this quantity would be non-zero, and hence if that non-zero quantity, we are calling it bias term. So bias is what? The difference between mean of estimator and the true value of parameter. So this is the bias term. So we express mean square error as a sum of variance plus a square of bias. So various bias trade-off you might have already heard in many of the learning problem, bias, variance, those things. So efficiency generally we measure through variance and bias. If the system happens to be unbiased, then there would be no bias component, only variance. So your mean square error would be directly equal to variance of the estimator. So that is the criteria. So a bias estimator can have a lower mean square error. Definitely it will have a lower mean square error if you observe some kind of biasness. Okay, so the most efficient estimator, or simply we call it best estimator, estimator, you can say that among a group of unbiased estimator is the one with a smallest variance. So which one would be the best estimator? The estimator which is having the least variance, which is having the least variance. Okay, so you are having several unbiased estimator, that means bias term is 0. that one is not contributing. Then among the unbiased estimator, how you can define which one is the best unbiased estimator? So which one that that estimator which is having the low variance or a smallest variance, that would be your best unbiased estimator. You may have a various unbiased estimator for a particular parameter, but among that, if you want to decide then which one is having least variance, that would be your best one. So I am taking one example here. Directly after that I will wind up today's class. So now we can consider, we can compare estimators and select the best one. For example, consider three different estimator of a distribution of data. Three different estimator I have taken. Just a plotting version I am taking. So this plot is talking about first estimator. It is the plot of first estimator against theta. Theta is the mean value here, this value theta, and value of a estimator is coming along this one. So this is the plot of theta, and that density plot, simply you can say that this is the density plot, and this is what this is with respect to another sample. This one with respect to first sample, this one is with respect to this one is so we are taking sample size of the same sample size, and this is the third estimator. This is the third estimator. The various estimator we are taking. So various estimator we can, so from these estimator we can observe that for estimator 1 and 2, the expected value, if you try to find mean value, you can see that it is just what, it is uniform in nature in this interval. You can say the uniform, it is having uniform distribution. So uniform, through uniform distribution you come with, and if you try to find the mean of this first estimator, this estimator 1, then mean definitely it would be in the middle of this interval, and that middle value is equal to theta. So you can say that expected value of the first estimator is equal to parameter. So very nice, it is unbiased estimator. Simply you can say that for first estimator we observe that mean of the estimator is equal to theta. Theta 1, you can say that first estimator hat theta 1 cap or hat, it is equal to theta. Also if you try to find and this mean of this estimator, more or like that would be also near to this value of parameter. Okay, and hence we can say that this estimator 2 is also unbiased. Now if we try to find mean of third estimator, this one, definitely mean would be here, and that mean is just right away from theta. So that means we are having a positive bias. So definitely for this third estimator we observe biasness. So there is a positive bias. Why? Because mean of this estimator is not equal to theta. That means the difference is positive. So it is positive. Estimator theta, third estimator is positively biased. So you can say that. So that's me. And so we will discuss among the unbiased estimator which one is the best. So we have to look into variance. So from the graph, anyone comment over that? Which one is having higher variance and which one is having lower variance? Variance means that variability of the data. How much data is varying? Variability of data. So which one is having high variance and which one is having low variance among unbiased estimators? So 1 and 2 are unbiased estimator. So here you can see that uh, 2 is having less variance with respect to first one. Remember that 3 is having least variance. 3 is this variability is up to this point to this point. So that's why 3 is having least variance. But that 3 estimator 3 is what that one is bias estimator. It is not. We are not going to use that much. But we will talk about estimator 1 and 2. Both are unbiased, and among that we can easily say that 2 is having relatively less variance and hence more efficient. So estimator 2 is more efficient than estimator 1. So that's why if you try to proceed with the estimator, you should proceed with this one. Estimator 2 is highly efficient. You can proceed with that. So other thing we will discuss in next class. Regarding attendance, you can put your attendance there in the comment box, and further